So hello everyone, I'm Somil Bansal and I'm a final year PhD student at University of California, Berkeley, working with Professor Claire Tomlin. Um, and during the course of my PhD, I have worked on several different aspects of Hamilton-Jacobi reachability, ranging from theoretical side of reachability to more like applied and practical side of things. But for the purposes of today's talk, I want to focus more on those applied side of things and kind of give you a flavor of the kind of things we have been doing to scale Hamilton-Jacobi reachability analysis for robotics applications in particular. So at a high level, my research deals with autonomous systems like these. And here we have surgical robots, autonomous cars, autonomous drones, as well as service robots. And all these systems might seem very different from each other at the first glance, but they have actually something in common. These are all safety critical systems. And as a result, we need to design algorithms that can actively reason about the safety of these systems as they work alongside humans or other robotic systems. And one such tool that we all probably believe in that can help us with this kind of safety analysis is Hamilton-Jacobi reachability analysis. So let me start with giving you an overview of the kind of things we have been doing before I dive deeper into the details. So on the first panel over here, we actually been using Hamilton-Jacobi reachability for safe multi-vehicle trajectory planning. So this is a project that we actually did in collaboration with NASA Ames, which was very interested in designing airspace for applications like drone delivery. So here, each circle that you see is actually a vehicle which wants to go to one of these four destinations. So these circles over here. And there are some obstacles in its path. For example, these could be the tall buildings that exist in the San Francisco environment in this particular case. And there is also presence of external disturbance like wind for these drones. And what we are doing is we're using Hamilton-Jacobi reachability analysis to make sure that each of these vehicles reach their destinations without colliding with obstacles or any other vehicle, despite the presence of disturbance. Now, in a lot of robotics application, we may not actually know all these obstacles beforehand. We may actually only be able to figure out those obstacles in real time, and hence we need to update the safety guarantees in real time as we sense those obstacles. So in the second or the middle panel over here, we are essentially using a learning-based planner, which typically fails and collides into this chair. But we are using Hamilton-Jacobi reachability analysis both to make sure that we can avoid these kind of failures of the learning-based system, but also we are updating this reachable set in real time to make sure that the system safely reaches its goal. And in this last panel over here, we are actually, the robot is actually operating in presence of humans. But as the human take any unexpected maneuver that is not explained well by the current human model, we use Hamilton-Jacobi reachability to reason about the confidence in that model and plan a backup safety maneuver for the robot. Now, today I want to focus on the first two of these panels. And first I will quickly chat about Hamilton-Jacobi reachability analysis and what it means. And I'm pretty sure all of you have seen this at multiple times by this point, but it would be good to quickly go through this overview to kind of set up the notations for the rest of my talk. I will then talk about how we can use Hamilton-Jacobi reachability analysis for safe multi-vehicle trajectory planning. And finally, I will come to the question of what we can do when we don't know these obstacles and our safety constraints beforehand, and hence we need to update the safety guarantees in real time. Now, to understand Hamilton-Jacobi reachability analysis, let's consider a very simple example. So here we have a robot and it wants to go to a goal position. And in this particular case, we want to make sure that the robot does not collide into any of this furniture over here. And the first step in Hamilton-Jacobi reachability analysis is to define a dynamics model for my robot. And here I'm using a very simple 4-dimensional model for modeling this ground robot, which consists of the X and Y position of the robot, along with the speed at which it is moving and the heading of the robot. But I've also added some disturbance in the dynamics, and which can capture any of the unmodeled effects. For example, a friction between the tire and the floor that we haven't explicitly accounted for in our dynamics model. In other cases, this could be the actual external disturbances that are present in the environment. For example, in the drone application that I showed early on, this could be the actual wind that's present in the environment. Then next, we define what are the states that we want to avoid. So in this case, we want to avoid all the furniture. So that's our obstacle set. Everything else is free space. So let's just see the same environment in a top view for simplicity. So here the gray region represents all the obstacles and white area is the free space. Now, given these unsafe states, we define a function L of x, which is negative inside the unsafe states and positive outside. And one such function for obstacles typically could be the sign distance function, which is negative inside the obstacle and positive outside. And then we set up a zero-sum differential game between the control and disturbance, where control tries to push the system, where the disturbance tries to push the system inside the obstacle over time as best as it can, whereas control tries to resist that and keep the system away from the obstacle as best as it can. And then we try to compute the set of states from which the disturbance would win and from which the control would win. And that solution is can be obtained by the principle of dynamic programming, which in this case gives us Hamilton-Jacobi Isaacs partial differential equation, where the differential equation is given by this, and the Hamiltonian captures the role of dynamics and control and disturbance in this dynamic programming principle. So let's just quickly see this dynamic programming principle in action. So we start with the terminal value function, in this case L of x, and then you see we are applying the principle of dynamic programming, and the value function slowly converges. And once the value function converges, the sub-zero level set of that value function is what we call backward reachable set, which also gives us the safe control to keep the system inside the backward reachable set at all times in this case. And quickly, this is the snapshot of the backward reachable set from the top view. So here the gray is the obstacle, the furniture in the environment, and the red is the zero level set of the of the value function, which is what backward reachable set is. So let me quickly pause here for a second and try to intuitively understand the shape of this backward reachable set in this particular case. Now, recall that backward reachable set is a sub-zero level set of the value function, which itself is a four-dimensional value function in this, which takes a four-dimensional input in this case, because it's a function of state, and state is four-dimensional. Now, what I'm showing you over here is actually a 2D slice of that value function or backward reachable set for a heading of π/2. So the robot is facing upwards towards the top of the screen and moving with some positive speed over here. Now, when the robot starts at this particular position, that means it has barely enough time to stop and avoid a collision with the obstacle in front of it. Now, if the robot starts at any position which is beyond this red boundary, then it cannot avoid such a collision. And those states are as doomed as the obstacle itself. And that's exactly what backward reachable set is capturing for us. And that's what this retraction in the boundary is indicating there. On the other hand, if the robot starts at this position, then it has a lot of time to stop and avoid a collision, and hence the obstacle boundary is hugging the backward reachable set boundary. If I were to see the same slice of backward reachable set, but with a heading of -π/2, meaning the robot is facing towards the bottom of the screen, then you will see a retraction in the boundary here, whereas the boundary of backward reachable set will hug the obstacle boundary in this region. Now, obviously, the idea of backward reachable set and Hamilton-Jacobi reachability is not just limited to this four-dimensional system. We can, in theory, apply it to any autonomous systems. And that's what we're going to see next, like how we can actually do that. So let me start with the first application that we looked into, which is of the safe multi-vehicle trajectory planning. And this is an important application in robotics for a variety of purposes. So, for example, people are interested into drone delivery. So this is a very much an application that Amazon and Google are actively working on. And then there are platoons of vehicles that people are interested in coordinating. And in all these scenarios, we need to solve the problem of multi-vehicle trajectory planning. Mathematically, the problem here is that there are a bunch of vehicles. So in this very schematic diagram, these are these aeroplanes over here, which wants to go to a given goal position. And there are some obstacles in the environment which these systems want to avoid. So again, for the drone delivery application, each of these could be a drone. they want to go to the house where they want to deliver the package. And this obstacle could be, for example, tall buildings in the city that they want to avoid. So our key question here is that how we can do trajectory planning for this system so that they reach their goal without colliding with the static obstacles like this gray one or with each other, despite the presence of external disturbances. And this problem is fantastic for the reachability formulation because we can actually, in theory at least, we can formulate the problem in the joint state space of all vehicles, and we can define the obstacle set in that joint state space as well as the target set that we want to reach, and we can get the solution out of Hamilton-Jacobi reachability analysis to make sure that the system to make sure that each vehicle reaches their target set without colliding with obstacles. And theoretically, it is great, but obviously the problem here is the curse of dimensionality. So for example, even for 4 vehicles with 3 states each, it takes, and this is just an estimate, millions of years to compute this reachable set. So certainly, this is a fine approach, but not scalable for robotics application. Now, in our work, we overcome this challenge by using the idea of sequential trajectory planning. So the idea of the sequential trajectory planning is that we assign a priority order to vehicles. So we have, suppose, n vehicles, and then we rank them 1, 2, 3 up to n, where the first vehicle is the highest priority vehicle. Now, this vehicle actually plans its trajectory to the goal without thinking about any other vehicle. So this is a much smaller dimensional Hamilton-Jacobi reachability problem that we can certainly solve. Then the second vehicle actually take the trajectory of the first vehicle as a moving obstacle and plan a trajectory around those moving obstacles as well as the static obstacles. The third vehicle take both the trajectory of the vehicle 1 and vehicle 2 and think of them as time-varying obstacles and plan a trajectory around that, and so on. So by doing so, what we have essentially done is that we have we have decomposed a reachability problem in the joint state space of n vehicles to n smaller reachability problems. And that allows us to significantly reduce this computational burden of Hamilton-Jacobi reachability. So let me show some results we get with the sequential trajectory planning method. So here, so this is the same video that I showed you early on in the talk, but here we are just kind of doing a simulation here in the Stanford in the San Francisco environment. So there are 50 vehicles that originate from this blue star over here, and they've been randomly assigned to go to one of these positions, which are different areas in San Francisco. And these buildings actually represent the tall buildings in the downtown San Francisco. So we want to avoid these black contours over here. And for the simulation purposes, we are using a very simple 3-dimensional model for each of the vehicle with the specs that are aligned with the present performance specs or the current performance specs of the drones. So to kind of give you a sense of the computation time, the reachable set computation per vehicle here takes about 200 seconds on level set toolbox. If you're not familiar with level set toolbox, this is an amazing toolbox developed by Professor Ian Mitchell during his PhD, and he's now a professor at University of British Columbia. And this 3-dimensional system over here takes 200 seconds to compute this backward reachable set, which means that for 50 vehicles, it takes about 3 hours. And for 200 vehicles, it would take about half a day. Now, even though we have significantly reduced the computation time from years to at least hours, this is still not sufficient for robotic applications. Because imagine that we want to replan for a certain region because maybe a new obstacle appeared in the environment, or maybe we want to plan around a commercial aircraft that's going through this environment. In all these cases, we cannot wait for 3 hours for each vehicle to replan their trajectory and go to their destination. So here, algorithmic developments alone may not be enough for the robotic application that we are interested in. We also have to think about the computational advancements in reachability. And so to that end, we have actually developed a new toolbox, which we call BEACLS, which stands for Berkeley Efficient API in C++ for level set methods. The idea of this toolbox is that it actually has one-to-one correspondence with the level set toolbox, which has been implemented in MATLAB. But now what we can do is we can actually leverage the advancement in the computational tools that is fueling machine learning these days for the reachability computations. In particular, we can actually parallelize the computation of the value function by using this concept of overlapping grid. And then that allows us to use the tools like GPUs to do this computation very, very efficiently. So just to kind of give you a sense of the computation savings we get by such an idea, this is the 200 second for the three-dimensional backward reachable set that I showed on the previous slide. If we only use this BEACLS library without any GPU acceleration, this computation time reduces to 33 seconds. But if we actually use GPUs, then it reduced to under 2 seconds. And this gives us almost 100-fold, I would say a factor of 100 is appearing in the computational savings in this particular case. So that reduces our computation time of 3 hours for 50 vehicles to under 2 minutes. And similarly, half of the day, the computation which was taking half a day now can be done within 8 minutes. So we have released BEACLS as an open source library, so you can actually download it and use it for your own problem. But additionally, we are now integrating ROS, which stands for Robot Operating System, with BEACLS. So any of you who have probably worked in robotics knows about ROS, and it's very important or very useful set of libraries and tools for robotic systems. So now we are integrating BEACLS and ROS together, so you can visualize these reachable sets and value functions in real time on your robots. Okay, so let me show some results. So now we took these advancements which were enabled by sequential trajectory planning algorithm and BEACLS, which is a computational method, and we combined them together for this 50 vehicle simulation scenario that I was talking earlier. So here we'll see 5 different simulation scenario. On the y-axis is we are varying the speed. So we are varying the wind speed, which corresponds to the disturbance in this case. And on the x-axis is the vehicle density. So how many vehicles are flying at the same time in the environment? So let me run all these videos at the same time, and then we'll discuss the results very quickly. So again, remember that each point here is a vehicle which wants to go to one of the 4 destinations which are randomly assigned to the vehicle. Black contours represent the obstacles in the environment that they want to avoid, and there is external disturbance, in this case wind. So first, one of the things that was very interesting that came out of this was this multi-lane behavior. So you can see like how the vehicles almost form 4 different lanes to each of their destinations. And here, the highest priority vehicle follows that lane first, or is kind of the leader in that lane, followed by the lower priority vehicles. Now, as you go to a high vehicle density, each of these lanes split into subsequent sublanes. And that's because there are multiple vehicles which are flying at the same time, and so they need to reach the destination almost at the same time. Consequently, they need to take different paths to the destination. But this gap between these 2 different lanes for any band of lanes over here depends highly on the wind speed. So for example, this gap is much higher when the wind speed is high versus it's much lower when the wind speed is low. And that's to make sure that in the presence of high disturbance, we need to make sure that any 2 vehicles are far apart from each other such that they don't collide even in the worst case disturbance. But the nice thing is that we never hard-coded any of these behaviors, these multi-lane behaviors or these lane-splitting behavior. These kind of behaviors emerge automatically out of the Hamilton-Jacobi reachability. So this is all good, but as you might have noticed, to do this Hamilton-Jacobi reachability analysis, I needed to know all those black contours, those obstacles beforehand. But the problem is, for future autonomous systems, that is very challenging. We may not know actually all these obstacles beforehand. For example, consider an autonomous car. Now, autonomous car needs to drive often around construction sites, blocked lanes, around humans. And we cannot possibly know all these construction sites beforehand going in the city. So in all these scenarios, we actually need to update our safety guarantees in real time as the robot encounters these obstacles. And the safety guarantees and updating them is not the only challenge for these kind of systems. In fact, making planning decision itself is very challenging when you don't know the environment beforehand. And one of the methods that people are exploring quite a bit in such kind of scenarios is machine learning based methods, which only make the matter of providing safety guarantees worse, because these machine learning methods can fail unexpectedly. So here, for example, is a video from Tesla Autopilot, which is pretty much a cliche in California at this point, but it is using a machine learning algorithm and could not detect that construction site and crashed into it. And we don't want these kind of things to happen for our safety critical systems. Now, in our lab, we don't have autonomous cars, neither do we have construction site, but here's a very simple example, which is kind of capturing the same idea. So here it is a mobile robot, which is using a machine learning algorithm to navigate to a goal, and it doesn't know any of these furnitures beforehand. But in this case, it collides into this chair. And that's because when we were using this learning algorithm, it hasn't seen the chairs of this sort. The kind of chairs that it has seen all have these straight legs. And consequently, it fails at this new kind of chairs. So a key question for these kind of systems is, one, how we can provide safety guarantees around these learning-based frameworks and how we can do so in real time. So let's chat about that a little bit. And our approach here to kind of encounter the challenges or to kind of counter the challenges is to monitor the output of the learning module, to recognize a failure in the learning module, and provide a corrective safe action whenever necessary. So what this means is that we will let the learning module whatever it wants to do unless the safety of the system is at risk, at which we will use Hamilton-Jacobi Reachability to provide the corrective safe action. And we will also constantly update our monitor in real time as we encounter new obstacles. Now, both of them seem very challenging tasks, so let me explain how we can do that. But before that, I want to quickly discuss the scenarios in which we are constructing such a monitor. So first, we assume that the environment is static. So it is still a priori unknown. So we don't know any of the obstacles, for example, in this environment beforehand, but it is a static environment. Second, we assume that the robot has a sensor which is perfect within its field of view. So as the robot encounters an obstacle, it knows that it is an obstacle. So once it senses an obstacle, it knows that it's an obstacle. Now there are some other works we have been doing where we are extending this framework to dynamic environments, where, for example, robot is operating in presence of humans, or when the sensor is not perfect, which is pretty much true for any real-world sensor out there. But today I want to focus on designing a safety or a safe navigation framework under these two assumptions. And to understand our framework, let's again consider a very simple example. So suppose the robot starts at this particular position facing upwards, and it wants to go to this green goal area in the environment. But this time it doesn't know this gray obstacle in the environment beforehand. Now, robot has a camera sensor mounted on it, in this case, just for illustration purposes, which is perfect within its field of view. So robot knows that within this light blue region, everything is free. Now, in light of when nothing is known about the environment beforehand, we treat everything that the robot hasn't seen as an obstacle. So we assume everything in this gray area is an obstacle. Now, obviously, that's a very conservative idea because we cannot even reach our goal. Our goal is an obstacle right now, according to our belief. But you will soon see that how we can, over time, refine this gray area while maintaining safety guarantees. But given this gray area right now, we can again use Hamilton-Jacobi reachability analysis to compute the backward reachable set. So that will be the set of all states within this red boundary. Now, just to remind you, this reachable set has the property that as long as the system starts inside this set, there exists a control to keep the system inside this set forever. Now, what that allows us to do is to make sure that the system never enters the unexplored part of the environment, which can potentially be unsafe for the system. And hence, we can make sure that the system would never lead to any collision. But moreover, inside this backward reachable set, we can apply any planner we like. So one of the nicest property about Hamilton-Jacobi reachability is its least restrictive control behavior. Inside the backward reachable set, it gives us the flexibility to apply any controller we like. So we can also apply the learning-based planner that the system might be using. The only time we need to apply the safety controller is when the system tries to breach this red boundary. So here, for the illustration purposes, I'm using a sampling-based planner within that backward reachable set. But consequently, the robot moves. And now, for example, it knows that everything within this light blue region is also free. So it can refine that gray area that it had seen earlier and compute a new backward reachable set. And it can keep doing so until the robot reaches the goal in a safe fashion. So let's see this framework in action. So robot initially start in some collision-free state. So that's the white area, and the red is the corresponding backward reachable set. Now, as I mentioned earlier, within the backward reachable set, we can use any planner we like. Now, at any time, if the system try to breach this red boundary, that's the only time safety controller intervenes and pushes the system inside the backward reachable set where our other planner can take over again. And this constant interaction between performance planner and the safety planner happens until the robot reaches the goal in a safe fashion. Now, this is great, but this framework requires us to compute this backward reachable set in real time. And we all know that's very challenging because of the curse of dimensionality. So let's see how we can potentially overcome that challenge. And our key idea to overcome that challenge is, rather than trying to compute the backward reachable set from scratch every single time the system encounters new information about the environment, we only locally update the safe set based on the new information. And what that means is, let's try to understand what that means with the help of an example. So suppose this is the snapshot of the environment at a particular time, and here the gray area is, the robot has explored the gray area, so it treats it as an obstacle, and the white is the free space, and orange is the corresponding backward reachable set. Now, as the robot moves slightly inside the backward reachable set, it discovers that this additional part of the environment is also free. So it discovers that this sliver is also free now. And for the sake of completeness, just to remind you, backward reachable set is just the zero level set of the value function. There are other levels as well. So as you go towards the right, you get more and more unsafe. As you are inside the backward reachable set, you are more and more safe. But the key thing to notice over here is that the only new information that we have obtained about the environment is in this sliver. So this is the epicenter of the information for the system. Consequently, we can only update the value function in this sliver and the neighbors around it. So here this Q, for example, is indicating the set of all states for which we want to update the value function. But the problem is that this analysis is based on the principle of dynamic programming. So as we update the value function in this blue boundary, this will affect the value of its neighbors, and then its neighbors, and then its neighbors. So this keep on expanding. So here I'm going to show you this computation, how that computation changes over time. At each time step, we update the value function within this blue boundary, and then we add the neighbors of that at that boundary and update their value function as well. So here is the snapshot of this computation changing over time. Again, at any given time, the states within the blue region is where we are updating the value function. And slowly you see that it increases in the time at first, but then the value function starts converging, and what we get is the converged value function. But the nice thing about this local update method is that you saw this blue boundary never touches the lower half of the state space. And that's where our computation savings are coming from. So first and foremost, we can prove that this somewhat intuitive idea actually leads to the guaranteed underapproximation of the safe set. And my belief is that one of the speakers earlier this morning, Sylvia Herbert, has actually talked about the details of why worm starting, that's the algorithm, that's what we call this algorithm, leads to the guaranteed underapproximation of the safe set. But more importantly, in terms of computational savings, the computation of 52 seconds for a naive full Hamilton-Jacobi reachability now only takes 0.9 seconds on levels at toolbox in MATLAB. But as I mentioned earlier, we now also have BEACLS, which reduces this computation time further by a factor of 100. And now we have the ability to compute this backward reachable set in under 9 milliseconds for a 4-dimensional system. And I will soon show how we can now actually deploy it on a real robot. But before that, I want to comment a little bit more on the local update method that we just discussed. So here we are using the local update method to provide safety guarantees in standard office environments that are static. But this is just a first step. We can actually use a similar framework in any scenarios where we don't know the safety constraints in the environment beforehand, and hence the safety guarantees needs to be updated in real time as we are going through the environment. So for example, suppose you started with some estimate of the wind, but as you were flying, you realized that the winds are stronger or weaker than you anticipated. Or in other cases, when you are working alongside humans, the human turns out to be more or less adversarial than you expected. In all these cases, we want to update the safety guarantees in real time, and we can use a framework like local update method to do so. In fact, we've been also working on this, particularly on this last direction of operating around humans. And as I mentioned earlier in my talk, and that's some preliminary work we will present at ICRA this year, but which I may not have the time to chat about today, but that is something I wanted to point out as well. So let's go back to the problem of safe navigation that we were chatting about earlier, and to kind of understand how this whole framework fits into this learning-based pipeline. Here I'm showing you just a snapshot of a generic learning-based pipeline. So here, for example, are the images of the environment, which are obtained from a camera sensor on board of the robot, which is then uses a learning framework for planning, and finally a control theoretic method for controlling the system. Now what we will do is that we will insert this safety monitoring scheme that we have just developed using the local update method. So this kind of is a filter over here. It does nothing when the control that's coming from the planning pipeline is safe for the system, meaning it never tries to breach that red boundary. But as soon as it tries to breach that red boundary, the safety controller intervenes and override the control coming from the learning side. So let's see this in action. So this is the same experiment that I showed towards the beginning of my talk, where if we don't use a safety framework, this robot collides into this chair. Now here, the robot is actually using a learning-based planner, so it uses this robot point of view image. So this is the first-person image that the robot is operating, is getting from this camera on the robot, and using that image to make decisions in this environment via machine learning. And now you will see that as the robot was trying to go towards the chair one more time, but this time safety controller intervenes and pushes the system away from the obstacle. And now the system is again inside the backward reachable set, where the learning controller takes over one more time and tries to steer the system towards the goal. And here you see this red boundary is actually being updated in real time from the obstacle information that is again obtained in real time from this camera sensor on board. So this red region, this backward reachable set in this case, provides this safe exploration region for machine learning, where we can perform learning without worrying about the safety violation on the system. Okay, so with that, I want to summarize what we discussed today. So the main goal of my research is to think about how we can scale Hamilton-Jacobi reachability analysis for a variety of robotics applications. In the first half, we saw how we can actually leverage the algorithmic advances along with the computational advances to enable Hamilton-Jacobi reachability analysis in multi-robot settings, which otherwise is very challenging task. Then we finally discussed how we can further use the Hamilton-Jacobi reachability analysis to update the safety guarantees in real time using the local update method that allows us to monitor the failure in the learning system and provide a corrective safe action whenever the safety is at risk of the system. So with that, I would like to thank all my collaborators without whom this work wouldn't have been possible. And I'm happy to take any questions that you have.
Yeah, thanks very much for this great talk. Any questions from the audience? you can raise your hand, and yeah, we can. Oh, yeah. Let me unmute you, Ian. Hello.
Hi.
Hi. Yeah.
Hi. Can you hear me?
Yes.
Excellent. Thanks, Somil, for the talk. I've seen a little bit of it before. I was wondering, in the last section where you were, well, I guess you also talked about it at the beginning, you were constructing these safe reach sets on the basis of map data coming in from sensors. Did you, I guess, how are you dealing with uncertainty in these cases?
So that's a wonderful question, Ian. Actually, so in this particular case, I'm assuming, let me go back to, maybe that. So in this particular case, we are assuming that the mapping data is perfect. So we are actually not dealing with this uncertainty, but I can tell you about some of the directions we have been taking since then to incorporate this uncertainty. And the first thing we kind of trying is that a lot of these mapping-based algorithms like SLAM also give you a measure of the uncertainty in the depth estimation. So the one simplest thing we can do is we can actually take that uncertainty measure and just use a different level of our value function. So instead of using a 0 level, suppose the uncertainty is 5 centimeter, then we can actually take the corresponding value function level.
You say the uncertainty is 5 centimeters. That's typically not what you get back from one of these state estimation systems, right? They're giving you, I agree with you that they give you an uncertainty, but they give you some kind of distribution of uncertainty, not a single number.
Right, absolutely. So I think what we are doing there is we are actually just kind of thresholding that distribution, say up to 2 sigma, for example, in this case. So we are not actually fully leveraging the stochastic nature of that uncertainty. We are converting that to deterministic uncertainty and using that, which certainly is an assumption we are making and mathematically not necessarily the right thing to do. And we may want to actually use the full distribution, but that's what we are doing right now to capture this uncertainty.
And so what are you doing with that information? Let's assume that you can get a hard bound on your uncertainty. What are you doing with that information?
So the one thing you can do right away is that so you still work with the same boundary of the obstacle, and but the nice thing is that through Hamilton-Jacobi reachability, you get different levels of the value function. But now, instead of the 0 level, you can pick the level 5 if this corresponds to 5 centimeter uncertainty, or the level 10 if it corresponds to 10 centimeter uncertainty. Because by augmenting the obstacle by that uncertainty amount is equivalent to just picking the different level of the value function at the end. Does that answer your question?
Okay, and then are you factoring in any uncertainty in your calculation of the reachable set? For example, uncertainty in your ability to actuate in a given direction?
Uncertainty in the, so meaning
is the reachable set, is there a game in there? Is it a robust reachable set, or is it just a reachable set?
It's the robust reachable set. Is the disturbance is added in the dynamics.
And what do you take into account on the disturbance?
So the disturbance actually, the disturbance in particular in this case, so what we did is we had this turtle bot and we designed a feedback controller for this turtle bot and we saw like what was the tracking error. So that's what we are using as disturbance in our dynamics model, which kind of capturing essentially how much I can follow the trajectory that is coming out of my model on a real turtle bot. So that's what it's kind of capturing there.
Okay, thank you very much.
Sorry, we have 2 more questions. Let me unmute Mauricio. Hi.
Hi. So thank you very much for your nice talk to these robot kind of applications. And I have a question regarding this connection between the camera and the robot and the reachable set.
Yes.
So as far as I can see from the simulation, I mean, you are showing what the robot is viewing, so the robot point of view.
Right.
But in fact, what I think you are doing is just to detect not the real scene, but the directions or a cone of directions, because I see a cone in blue appearing on the right-hand side of the screen.
Right.
So are you really reconstructing the scene? In which case it's rather complicated because you just have one image.
Right.
Or
so
you're just detecting obstacles in a different way. Or combining, for example, distance sensors and the camera.
I see. Okay, so good question. So the answer is that we are actually building the map. So we are actually detecting the obstacle. This cone is a simulation that we created after the fact for illustration purposes. So this cone may actually have some errors. I didn't pay much attention to that. But the way it is actually working is that this camera over here has two modes. So one is an RGB camera as well as a depth sensor on it. That RGB camera's output is what I'm showing you here, which the robot is using for planning purposes. So this is feeding into the learning-based planner that, again, we developed in some of our other works. And then the depth information that you're getting out of it is actually being used for building up the map in real time. And that's what we're using for the backward reachable set computation.
Okay, so you're a depth sensor.
Yes. For the occupancy information, yes.
Yeah, okay. Okay, this can be much more interesting because if you were just using cameras, then the situation would be much more complicated because with two cameras you are able to reconstruct the scene, but then this requires the solution of the photometric stereo problem, which is another additional numerical issue. Right.
Yes. So yeah, definitely. And I think in fact even with the depth camera, we have some of those issues because ultimately what we get out of these depth cameras is a point cloud. So it's not a function, it's a point cloud. So we are still incurring some of the numerical errors, which I think Ian hinted at in his question. So those are still there, but it's very interesting to see the effect of those on the safety, which we haven't done yet so much.
Okay, thank you very much.
We still have one more question, I think, from Massey. Let me.
Yes, thank you. Thank you for the talk. So I have just one simple question. So I was wondering, regarding like safety control, so I was wondering how it compares to the control barrier functions. I mean, I know that there are pros and cons for each one, but what are your thoughts about that? I mean.
Sorry, so you're saying what are the pros and cons of this the safety versus a function? Which function are you talking about?
The barrier control functions,
control barrier functions, yes.
Yeah.
So the control barrier function, I think it's totally a viable approach in this particular case. In fact, we are now deploying this framework on a working robot in collaboration with Professor Koshil Srinath at Berkeley, who works on working robots. And there we are using control barrier function. The biggest challenge or the difference between control barrier function and reachability is that control barrier function gives you only locally optimal solution. In particular, when you have control bounds and disturbances, the Lyapunov inequality that we solve in control barrier function may not be feasible. And hence, you may not be able to maintain the safety. So what we are doing there, for example, is we are actually using we're only computing an approximation of the backward reachable set and using that as the barrier function itself.
Oh, okay.
Which can be pretty interesting because you saw this jerky behavior in this video when I played that video, and that is because of this bang nature of Hamilton-Jacobi Reachability solution, which we can overcome by using control barrier function or other optimal control-based methods.
Oh, great! Thank you so much. Thanks.
Thank you.